So now I'll take a quick look at the IPC methods that we haven't really looked at, meaning that I'm not going to go back over the use of mutexes to use shared resources, because in the mutex example I did exactly that. And so that is one of the main IPC methods. If you wanted to have like a global variable shared around your program, you could lock it, right? And then just use your mutex sort of standard of taking, modifying, and giving with the mutex to do thread safe modification of a global variable. On top of that now, I'm going to look at task notifications and queues. So we'll start with queues, as they're sort of the simplest, and they, if the queue API and the task notification API are very similar. So queues, like everything essentially in FreeRSOS, they take a handle, or you need a handle to sort of reference the queue object which you're wanting to then use. So we'll just call this my queue, right? And we'll create it as null. And so in my main, I'll create my queue. And so therefore say my queue equals, and this queue creates, I think. Yes, and so it takes in two arguments. We take in the length, so that's the amount of entries, and then the size of each item. So let's say I want to send integers. I'm just going to make an arbitrary length of like 10, and I'll use the size of operator to get me the size of int. Now this could be anything, a structure, an array, whatever you want. But here, I'm just wanting to send integers. And so what I'm going to do is I will then, in task 1, send values to task 2, and I'm going to send a few of them. So then what I'll do is every 1 millisecond, task 1 will run, and let's just say for int I equals 3, I equals 3, goes 0, I less than 3, I plus plus. And so what I'll do is I'll just send, or so I'll put an integer here. So this is int my temp int. And so this is the integer that I'll use to store the value I want to send. So I'm going to fill this value, this variable, and then I'll get, through the use of the queue calls and the queue API, this value's data will get copied into the queue. So then in here, I can use the FreeRTOS, like there's a call to get the systicks, if I can remember it. Get tick count, this one, I think. So this returns the current systic count. The systic is constantly increasing and actually has for each tick a value associated with it, which you can use to do certain things in regard to time. If you know that your systic's a millisecond, then you can use it to deal with milliseconds. There's also a macro to convert ticks to time, but we can just use this directly. And all I'm going to do is I'm going to send, I'll firstly set my temp int to the current tick, and then I want to copy it into my queue. And so to do this, I'll just use the queue send here, right? So it takes in the queue reference, the item to send, and then the ticks to wait, right? And so what I'm going to need is I'm going to send it into my queue. I need to put in a reference to the data, my temp int, and the time to block. And so this is the same as like with semaphores. It's either going to be pretty much indefinitely or 0. And then if you look at the documentation for xQsend, it will return whether it was successful or not. And so you can use this similar stuff when you use semaphores to say, oh yeah, they successfully sent, do this, it didn't send, do this, or don't do that, or whatever have you. You know, this is the functionality they provide you to use blocking and return values to do whatever it is you need. So I'm just going to put in port max delay. Because in this case, all I wanted to do is to send, and so if the queue's not available, I essentially just wanted to wait and then send. So I think I've just accidentally copied it. So exactly here. So what this is going to do is it's going to send the current tick value 3 times. So this will be 3 times the same number, right? But we don't really care what we're sending. I just want to show the functionality. And then what we'll do is it will receive this in task 2. And so when I was talking about tasks and how they're sort of implemented, I was saying that they're sort of like an a continuous loop, and unless you want them to sort of take over the CPU and just bombard it with looping, which sometimes is required, they should generally have some sort of a blocking condition, right? Like whether they're waiting on a delay or whether they're waiting on information from a queue or something that triggers their execution. And so in this first task here, I have this delay. So it's not going to execute on an infinite loop without breaking, because it's going to hit this every execution and delay for a tick. So it's going to actually invoke the call, it's going to call the scheduler after it's finished one cycle of execution. Similar to this, I don't necessarily always have to have the delay within my tasks. Another way is that I can just use the blocking of a queue, of like a receive or a task notification or a semaphore, like I showed in the semaphore example, to actually remove the need for a delay, right? To sort of interrupt this spamming of execution. It's not always desirable, right? And so I'll do that exactly here. So if, so I'll take in a temporary variable to store it in. So I'll call this int my temp int. Now I want to receive the variable and check that I received it, right? So I'll say if xq receive here, my queue, where am I going to store the data? I'm going to store it in my temp int. And does it require anything more than this? I have to strictly check the API documentation. Queues, bring this across. So receive, does it just take in, oh, and it ticks away, it also has a block time, which makes sense. So we'll also block on this indefinitely, right? And then what we'll do is we'll check the return value, PD true if it was received correctly. So equals PD true. Cool. So if we hit this point, we know that we've successfully received a value, so then we can print it because we know that it's populated. Printf receive right, okay. Else we'll just say it's receive failed, right? But we should never really hit that. I kind of see a circumstance where that would happen on the system. So let's give this a quick run. Hopefully I haven't forgotten anything to make this run. And see, as our tick's going up, we can see that we're sending the value 3 times. Some weird sort of init stuff happening at the beginning here, but as it sort of gets more consistent, we can see that this loop here is just sending the current tick value 3 times to the queue. And this guy is waking up and sending the receive value. So we can, for instance, put in here, yeah, so sorry. This guy is actually waking up 3 times per tick, which we can see, because what it's doing is it's receiving this, then it's going to do this, and it's going to keep going further, and it's going to run while again, and it's not going to wake up again, but it's going to execute this code 3 times per tick until he's read everything out of the queue, and the queue is empty, and he'll then block, right? And so he hasn't been able to get anything, and then he'll block, and so we're getting 3 executions per tick, because we're reading in the 3 items we send here until there's nothing left, and then it will block. So that's pretty much the complete use of a queue. I mean, they're very simple. You can get more creative if we look into sort of like all the different overrides, and there's peaking and all of this sort of stuff and sending to front. But the basic principle is the same. You're sort of creating a buffer and you're sending and receiving from it, right? And you just need to have a reference to the queue. So you need this queue handle from your different tasks to sort of be able to interact with the queue objects, right? So now we'll get into the task notifications, which are slightly more involved. And so what we'll do is we'll use demo task 3 as a receiving task to receive from a task notification. And so every task has a task notification. We don't need to create it, right? So it's inherently part of each task. And so to notify a task, we use this this xtask notify. And if we look at sort of the arguments, we say, yep, the task we want to notify, so this is the handle. So if we want to send from task 1 to task 3, we would use this handle that we created up here. You know, I want to send to task 3. We'll send the value. So this is the the value that's going to be used to update the notification value given this action. And so this is the action I said in the lecture. We can have sort of like, we can do a bitwise OR, bitwise AND, we can clear it, we can increment it, you can do whatever you want. You can choose the action from here. They all make a lot of sense and they're all explained. It's quite simple, really. So let's say we just want to notify and increment, or let's actually maybe increment a bit boring. What else could we do? Maybe we could constantly bitwise OR the current tick value with itself in the notification. So it's going to give us some sort of a complex increment functionality. So we'll send this queue send, and then we'll just put in here as well, we'll just send one task notify. So what we're going to want to do, we'll look at the API documentation, x task notify. Now we're wanting to send, or we can just do a basic check, because this is always good. We'll put that at the end. So we're sending to handle 3. So this is the handle that we use to reference task 3. It's taking in a value, and so what we can do is we can just go x task get tick count, which means I'm going to pass in the value of the current tick and the action that we want. Now, FreeRTOS defines these by using these sort of human readable flags. Now we want to do set bits. The notification is subject task will be bitwise ORed with its value, right? So the value will be ORed with this new value, meaning bitwise. So then we can go eset bits. That's the flag. Oh, sorry, we need to do a check if equals PD true. Then we can say, oh, we don't even need these because it's a single line. Printf task notification sent. Right. So there we've got the sending setup. Now, the same goes for in task 3 with in task 2, that we can use the actual receiving of the task notification, this task notification take, because it works the same way as a semaphore, you need give and take, to block. So here we have the clear flag, so this one here, which will be explained here. In here, all we have to do, say if an RTOS task notifier is received and x clear count on exit, this parameter is set to PD false, then the RTOS task notification is decremented before blah 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 exits. This is equivalent to valuing the value of a counting semaphore before decrementing on excessive blah blah blah. So if it's set to PD true, then the task notification's value is reset to 0, right? Meaning we don't want to set it to 0 because we want to keep incrementing it. We want to keep ORing it with this new value we're sending. So we'll put in false in the first one, and we want to then block forever, because why not, right? So we'll say if, it's same again for the, what's the return value? The return value, the value of the task notification value before it's decremented or cleared, right? So here, we say like int, or we have a uint32, which on my system is an int. So int task val, or notification val, and so if, and then what we'll do is a double bracket, so if task notification val, and so what this line actually does by doing these extra brackets, I'm saying my conditional statement is that if this value was set to something, if this means if this value has a non-zero number, and because I'm going to do a print statement and I haven't initialized this to something, so I'm sort of making sure that I'm always going to print a valid integer, right? Meaning I'm only going to print if I've actually received something and updated this value to a non-zero number. So here we have x, what's the x, ul task, oops, where am I? Ul task notify take, clear counts on exit, no, I want false. Was it? And ticks to wait, which is going to be port max delay. Now, if, so there we go, printf task notification So there we should get the notification value from the task notification API. We're not clearing it, and what we're going to do is we're going to print the receive value. So if we make this, I don't know exactly the sort of random numbers we'll get, but here we go. Whatever this is. So I guess what it's doing is it's just constantly taking the notification value, because if we look here, if the notification is received and is set to false here, then the task notification value is decremented before this call exits. So we must be getting 21, which makes sense because this is the tick. And then what it does is it constantly decrements it. And so it keeps taking, like I'm doing while this, and so it can continuously get it until it's no longer getting a value in here, until this value is equal to 0, so that this conditional fails. And so because this is constantly getting called, it's constantly decrementing, and therefore this is why we get this sort of random countdown, which is obviously started from a lower value and decremented down, decremented down. So that makes a lot of sense. So I think this should make a lot of sense why how we use these. So I was just quickly wondering why the this doesn't block indefinitely, but then I was reading through here, which I sort of missed. Where was it? Yes, here. Optionally block to wait for a task notification value to be non-zero. And so that must be why it's automatically decremented, because if you just send a task notification, it gets incremented to 1, and then it returns on the take and goes back to 0, and then it will block indefinitely. So then it has the normal functionality of a semaphore. So I hope this helps, and next we'll start to look at software timers.